Hi everyone, welcome to a new lecture series on control of mechanical systems. We see many mechanical systems in our day-to-day life such as automobiles, aerospace systems, robots, various machines used in industries, etc. In this lecture series, we will be focusing on control of such mechanical systems and we discuss the design and simulation of various control schemes. In this first lecture, we give a brief introduction to the mechanical control systems. We start with a discussion on the various components of mechanical systems. Then we give a brief introduction to the modeling and control of mechanical systems.
Mechanical systems are used to perform a specific task that involves motion of mechanical devices. Examples of mechanical systems are automobiles, aerospace vehicles, robots, machines and lathes, etc. We can see that all of these systems are associated with some motion of mechanical devices. So, the physical variables that we are interested in a mechanical system will be either position or velocity of the whole system or certain components of the system. This lecture series is about control of mechanical systems, in which we discuss various control schemes or algorithms to improve the performance of the systems in terms of accuracy, stability, lesser energy requirement, etc. Mechanical control systems consist of a mechanical system or machine along with a feedback control system for controlling its output. The major components of the mechanical control system are the mechanical system or plant, controller, actuator, and sensor. Figure 1 shows the general block diagram of a mechanical control system. Here, the actuator, plant, and sensor are combined together and which we call as the system or the dynamical system. And we have a controller which is used for controlling the physical variables of the system which we are interested. Here, the actuators and sensors are basically transducers which convert energy or signal in one form to other form. The actuator basically transforms the control input, which is usually an electrical signal, to some mechanical input to the plant. And the sensor transforms the mechanical variables in the system to some electrical signal, which is then used for comparing with the reference. The mechanical system usually consists of the elements such as mass, spring, damper, etc. The mass and spring basically stores the energy, which is in the form of either kinetic energy or potential energy, and the damper is an energy dissipating element, which dissipates mechanical energy. These elements are basically linear elements which can be represented using a linear input-output relation. And similarly, we can have nonlinear elements as well, such as gear with backlash and nonlinear spring, etc. Now, the role of the controller is to compute the control input to the system. The control input is then used for controlling the physical variables of the mechanical system as per the requirement. In other words, the controller is basically used for improving the performance of the overall system in terms of accuracy, stability, lesser energy requirement, etc. In general, the controllers are some algorithm that uses the plant model and sensor information for computing the control input. Based on the type of implementation, controllers can be classified as either analog controller or digital controller. In analog controller, the control algorithm is implemented in an analog circuit such as passive electric circuit, operational amplifier circuit, etc. Whereas in digital controller, the control algorithm is implemented in a digital circuit such as microcontroller, digital computer, etc. In mechanical control systems, sensors are used for measuring the physical variables of the system that we are interested. And these variables will be usually position or velocity of some components of the system. The variables that we are measuring using sensors are called as output variables, and the minimal set of variables that capture the entire dynamics of the system are called as states. In most of the cases, the output will be some subset of the states, or it can be a function of the states. And we usually use estimators for estimating the entire set of states from the output variables. Actuators are used for obtaining the mechanical input to the plant from the control input signal, which is usually an electrical signal. The basic types of actuators are electromechanical actuators such as DC and AC motors, magnetic actuators which are used in magnetic levitation systems, pneumatic actuators that converts control input to some pressure input, and hydraulic actuators which converts the control input to some flow input using pump. Next, we move on to the modeling of mechanical systems. We use mathematical models for analyzing the behavior of mechanical systems and designing various control schemes for adjusting its behavior. In mechanical systems, we are interested in the change of position or velocity of the system with the time. The behavior of the physical variables in the mechanical system with the time can be represented using differential equations with the time as the independent variable. Therefore, in this lecture series, we will be mostly dealing with ordinary differential equations, and our objective is to compute the forcing input to the differential equation, which is actually the control input to the mechanical system. Now, the task of representing the mechanical system using some mathematical equations is called as the mathematical modeling of the system. In mathematical modeling, we use various physical laws such as Newton's laws of motion, energy balance equations, etc. to obtain the mathematical representation of the system. This is also called as modeling from first principles. In general, mechanical systems can be represented mathematically using either time domain models or frequency domain models. In time domain modeling, we mostly use state space models, which is in the form of a linear or nonlinear state equation. And in frequency domain modeling, we mostly use transfer function models, which is an input-output model in the form of a polynomial fraction. The mathematical model should be sufficient enough to capture the behavior of the variables in the system that we are interested. And we use the mathematical model for designing the controller, or in other words, designing the algorithm for computing the control input to the system. When it comes to the control of mechanical system, the main objective is to achieve the desired performance of the system in terms of faster transient response, lesser control effort, stability, etc. In this lecture series, we will be mainly focusing on the control schemes such as proportional integral derivative controller or PID controller, linear quadratic regulator or LQR, sliding mode control or SMC, model predictive control or MPC, etc. We will also discuss the simulation of these control schemes for various mechanical systems such as DC and AC motors, simple pendulum and inverter pendulum systems, mobile robots, aircraft systems, etc., for which the MATLAB codes will be provided. That completes this lecture. Thanks for listening.